Welcome to B2S Academy. Welcome to my maths class. Today, the continuation class of the chapter Permutation and Computation. In this episode, first I work out few sums. Then I shall discuss few theories and continue. Okay. First of all, these two sums. Number one. 4 minus x p2 is equal to 6. We have to find the value of x. Already you have learned this. NPR is equal to factorial n minus r. I will suggest students, learners, in the initial stage, you may write down this on right side of the sum, or factorial 4 minus x divided by factorial 4 minus x minus 2 is equal to 6, or factorial 4 minus x by factorial 2 minus x is equal to 6. Now 4 minus x is greater than 2 minus x, therefore I write factorial 4 minus x like this: 4 minus x, 1 less than this one, that means 3 minus x. Then we have 2 minus x, factorial 2 minus x, rather I write that factorial 2 minus x is equal to 6. Now these two will be cancelled, since factorial 2 minus x is greater than equal to 1, therefore we can cancel, or 4 minus x into 3 minus x is equal to 3 into 2. Now already I have discussed to solve such equations as factorial symbols are there. Therefore 4 minus x, 3 minus x are two successive natural numbers. Now 4 minus x is greater than 3 minus x. Then we can compare any of these two factors with the corresponding integer on the right side. Since it is greater than this, therefore from this we can write 4 minus x equal to 3, from which we get x equal to 4 minus 3 equal to 1. Also, since it is quadratic equation, you can solve this equation by using the method of solving quadratic equation. 12 minus 7x plus x squared equal to 6, or x squared minus 7x minus 6 plus 6 equal to 0. Now this can be written as x minus 6 into x minus 1 is equal to 0, from which we get x equal to 1, 6. Now we have to check which value is to be accepted. For x equal to 6, you see 4 minus x is there. 4 minus x is negative, therefore x is not equal to 6. Therefore, finally, x equal to 1. This is the answer. Follow uh, the argument I have used while I have used this method. And if you want to solve the quadratic equation, then you will get two values of which two may not satisfy the conditions given. You have to reject one in that case if it is not satisfying. Now I solve this sum number 2. N plus R plus 1 P2 is equal to 72, or factorial N plus R plus 1 by factorial this minus 2, that means N plus R minus 1 is equal to 72. Now, numerator can be written as N plus R plus 1 into N plus R into factorial N plus R minus 1. You can mention here, since factorial N is equal to N into N minus 1 factorial. It is better to mention these things in the initial stage. By factorial N plus R minus 1 is equal to 72. Now these two cancelled, and on the right side you mention factorial N plus R minus 1 is greater than or equal to 1. Therefore, we get finally N plus R plus 1 into N plus R. You see, this is product of two successive numbers. The first factor is greater than the second factor. Now I write 72 as 9 into 8. These are also two successive numbers. Smaller one is 8. Therefore, comparing, we can write N plus R is equal to 8. This is number 1 equation. Now, the other one, N minus R P2 is equal to 12. From that, we get factorial N minus R by factorial N minus R minus 2 is equal to 12, or numerator I write like this, N minus R into N minus R minus 1 into factorial N minus R minus 2 divided by factorial N minus R minus 2 is equal to 4 into 3. I have used similar argument. Therefore, N minus R minus 1 is equal to 4 into 3. Now, using similar argument we have used in these cases, we can write N minus R is equal to 4. This is equation 2. Thus we have got N plus R equal to 8, N minus R equal to 4. Now, 1 plus 2, adding these two, what we get? 2n is equal to 12, therefore n equal to 6. Putting n equal to 6 in 1, what we get? 6 plus r is equal to 8, from which r equal to 2. Therefore, finally, we get n equal to 6, r is equal to 2. Factorial 2n is equal to this expression. LHS 2n factorial, that can be written as 2n, 2n minus 1, 2n minus 2, 2n minus 3, 2n minus 4. I write last 4 digits, that means 4 into 3 into 2 into 1. To prove this, first we note the first part is 2 to the power n. That means that is product of n numbers of 2. Now, after writing in expanded form for 2n factorial, we note the odd places, numbers occupying odd places. What are those? 2n, it has one factor 2, then 2n minus 2, it has one factor 2, then 2n minus 4, it has also 2 as one factor. Now I write this 2 into n, no need of putting second brackets. Here I need second brackets, 2 into n minus 1, 2n minus 3, 2 into n minus 2, dot dot dot. In place of 4, we write 2 into 2 into 3. In place of 2, I write 2 into 1 into 1. Now I write together all the numbers occupying odd places. That means these are taken together. That means now as one factor of each has 2, then we take all those 2 together. That means how many 2's are there? Since total number of factors is 2n, therefore numbers occupying odd places will be in n numbers. Therefore, there are n numbers of 2. We take those 2 together, that is 2 to the power n. Now, for the odd places, I write other factors, which are n from this n minus 1, from this one n minus 2, finally 2 into 1. Follow this. Then I write other factors. That means if I start from 1, that means ascending order, 1 into 3 into 5 into dot 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 into. From this n minus 2, from this n minus 1, sorry, from this 2n minus 3, then 2n minus 1, first of all we have taken all the numbers placed in the odd places. Since each of those have 2 as one factor, we take all n numbers of 2's together, that is why 2 to the power n. Then I have written other factors within second brackets. Then in this part I have written all numbers placed in the even places. Therefore finally 2 to the power n, and this is nothing but factorial n factorial into this one. Thus we have got the right hand side. Therefore R H is root. Thus this sum is finished. Now number 4. First I write the left hand part. 1 plus 1 into 1 P1 plus 2 into 2 P2 plus 3 into 3 P3 plus dot 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 plus n into n Pn. Now first I remove or write the value of 1P1, 2P2, 3P3, etc. 1 plus 1 into 1P1, 1P1, that is equal to factorial 1 by factorial 0, that means 1, 2P2, that will be factorial 2 by factorial 0, factorial 2, like this, that is 2. Therefore, here it will be 1 plus 2 into 2 plus 3 into, I write here factorial 2 rather. Though 2 and factorial 2 same there, but factorial 2 I write, and this will be 3 into factorial 3 n into factorial n. Now this is 2 plus, I write this 2 as 3 minus 1 into factorial 2. This 3 as 4 minus 1 into factorial 3. And this one as n plus 1 minus 1 into factorial n. Now you may ask why we are writing like this. Actually here factorial 2 is there. Now if I multiply it with 3, then we shall get factorial 3. Again factorial 3 is there. If I multiply it with 4, then I shall get factorial 4. You see, 4 into factorial 3, that will be factorial 4. Now why we are writing that will be clear from the next step. This is 2 plus 3 into factorial 2, that is factorial 3 minus factorial 2. You see, you can mention here since factorial n equal to uh, n into factorial n minus 1. Therefore, if I get n into factorial n minus 1, I can write easily factorial n. I have used that idea. This is 4 into factorial 3 means factorial 4 minus factorial 3 plus next one will be similarly factorial 5 minus factorial 4 plus dot dot dot. The last one will be factorial n plus 1 minus factorial n. Follow this. Now 2 factorial 2 will be cancelled. Just I rub this one. You note factorial 3 positive, here it is negative, factorial 4 positive, here it is negative. Therefore, we can group like this. Now, in the earlier group, there will be plus factorial n. Therefore, the last but one group will be factorial n minus factorial n. Only this will be there, only one. Now, two numbers within the brackets will be cancelled for each group. Therefore, just this one will be there. Follow the technique. Therefore, we get the RHS part. Now, RHS part is n plus 1, Pn plus 1. Therefore, just we mention here as n plus 1, Pn plus 1 is equal to factorial n plus 1 by factorial 0, which is factorial n plus 1. Or we can add this step here. Therefore, the sum is solved. After learning the chapter permutation and combination, we shall move to the very important chapter probability. That is why I have taken this sum tossing based on tossing of coins. Actually, in probability theory, we shall use different events, tossing of coins, rolling of die, etc. That is why I have chosen this sum. Here, a coin is tossed 3 times. Also, it can be said 3 coins are tossed once. Same thing. And the outcomes are recorded. That means head, tail, head like this. The question is, how many possible outcomes are there? I discuss this problem here. First, let me do the rough work like this. Say we get head in the first row. Head is denoted by the symbol H, tail is denoted by the symbol T. Say we get head in the first row. Now, in the second row, we shall get head in the corresponding third row. It may be head. For head in the second row, third row, we may get tail. Then, if we get tail in the second row, then in the third row we may get head, and if we get in the second row tail, in the third row we may get tail. Therefore, first for one outcome in the first row, we are getting here totally 2 into 2, 4, 1, 2, 3, 4, corresponding to head in the first row. Total outcomes we can record like this: H, 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 T, H, T, H, H, T, T. That means total outcomes 4. Now I explain here. For the outcome head, I write short symbol and the full form. For the outcome H in the first row, possible outcomes are H and T in the second row. Therefore, for two outcomes in the first row, total outcomes in the first two rows is 2 into 2. Again, for one set of outcomes possible outcomes in the third through is 2. Therefore, total number of outcomes will be 2 into 2 into 2. For the first two, 2 into 2. Now if we consider the third one, 2 is to be multiplied with the previous result. Total number of outcomes will be, that is 8. We can consider the use of the formula in PR using NPR formula. Total number of outcomes 2p1 into 2p1 into 2p1. Out of two outcomes, that is 8 and 12, one will be obtained in the first. Similarly, one will be obtained in the second, and one will be obtained in the third. That is 2p1 into 2p1 into 2p1. The result will be same. Now I am going to discuss few theories. Already I have started in the earlier episode restricted permutations. Now there are still few restricted permutations. I call it case 3. We have to take our things together and arrange. Restriction is of those R things, K things have already occupied specific positions. Let me draw these diagrams to say these are K things out of R things. Still there few. This is neet. Now the restriction is K things already occupied specific positions. That means they cannot change their positions. That is, they are occupying fixed positions. Then number of permutations will be how many? Since K have occupied specific positions, therefore we have still total number of things N, and already K things have been placed in specific K positions, specific K positions. Note this term. Therefore, those things placed in K specific positions cannot change their positions. Therefore, out of remaining n minus k things, we have to take r minus k things, and the number of arrangements, required number of arrangements will be that number of arrangements taking r minus k things out of n minus k things, that is required number of permutations is equal to n minus k p r minus k. Note two things. Initially, k things are placed in specific positions. That means they cannot change in themselves their positions. Hence, the positions of k things put earlier is fixed. Then we have n minus k things in hand, and since totally r things are to be taken, that means from those remaining n minus k things, we have to take r minus k things and permute. Therefore, required number of permutations is this one. This is first case. Now, if those k things placed in the early stage can change their positions, that means they can be placed in any order. In that case, if k things can arrange in themselves, that is, they can be arranged in any order. Then total number of arrangements will be n minus k p r minus k into k things which can permute in themselves in factorial k ways. Therefore, in that case, total number of arrangements will be this one. Then case 4. Again, total number of different things n, and k things will be together. In this case, k things will occupy specific positions in the first case, and in the second part, k things can arrange in themselves. That means they can be arranged in themselves. Now, in this case, r things will be k things out of r things will be together. That means in place of k things, out of n things, r things are taken in which k things are together. Then what will be the number of arrangements? These k things, since they will be together, therefore we can think in place of k things one entity or one thing. Then total number of things will be n minus k plus one thing. We subtract k things first from the total, then in place of those k things which will be together, we have to consider 1, therefore total number of things will be n minus k plus 1. From that, we have to take remaining r minus k things. That means number of permutation, total number of permutations is equal to r minus k plus 1 into n minus k p r minus k. In place of r minus k, we put one element. That is why total number of permutations will be this. K things together, that is why total number becomes n minus k things. Out of those we are taking r minus k things, and in place of k things we are taking one thing. Therefore, total number of permutation will be this one. Next, restricted permutation. I call it case 5. Here, total number of different objects n, taking all objects. In the earlier cases, we have considered r objects to be taken out of n different things. Here, all objects are taken and arranged. Now, if k things together, k things out of those r things, those are to be n things, all of n things are to be taken together to permute, of which k things will be there together always. This is first case. Then if we subtract this from the total, then we get n minus k objects. Now for k things which will be together, we can take that number as 1. Therefore, we get n minus k plus 1 objects. Those are to be permuted. In that case, total number of permutations these are to be permuted first. That means this one factorial n minus k plus 1, of which k things are together. Now those k things can arrange in themselves in factorial k ways. Therefore, required number of permutations will be n minus k plus 1 factorial into k factorial. This is the first case. Here k things always together. Now the other case is k things never come together. Now this one will be obtained by considering first arrangement of n things, total number of arrangements of n things taken together, that means factorial n, and number of permutations where k things are together. If we subtract this from the total number of permutations without restriction, total number of permutations in this case is equal to number of permutations of n things. Already we have mentioned in different things minus number of permutations where k things are together. That means factorial n minus n minus k plus 1 factorial into k factorial. Note this, not so difficult, the last part. K things are together here always. Therefore, in place of k things, we can consider one thing. That means total number of things become, in that case, n minus k plus 1. They can be arranged in n minus k plus 1 factorial, and in which k things are together there. Those k things can be permuted in factorial k ways. Therefore, required number of permutations will be, in that case, n minus k plus 1 factorial into k factorial. And here, k things will not be always together. That is why in this case, total number of permutations will be obtained by subtracting this one from the total number of permutations of n different things without any restriction. That is why this one. Now I shall work out few more sums on permutation. I have taken this one first. How many arrangements will be obtained if all letters of people are taken together? First one. And second part is, in these arrangements, how many will not have two keys together, side by side? Two keys together means side by side. Solution. First, you write down the word given. P-E-O-P-L-E. Number of letters. 336. There are two P's and two E's. Note this. Two P's are there, two E's are there. Others different. Now to solve this sum, let us recall that formula. If out of n different things, p things are of one kind identical, q things are another kind identical, and r things third kind which are also identical, then taking all n articles together, number of permutations will be factorial n divided by factorial p into factorial q into factorial r. I have discussed that in the earlier episode. Taking all letters together, total number of permutations is equal to factorial 6 by factorial 2 into factorial 2. Following this formula, now we simplify that. 6 into 5 into 4 into 3 into 2 divided by 2 into 2. Here 2 p's are there, 2 e's are there, therefore total number of permutations is this. Now this is the answer of the first part. Second part, how many in these arrangements, how many will not have two p's together? For that we consider two p's. Two p's are taken as one entity. We are not writing here letters. Those two are taken one entity. But there are two E's where there are two E's. Therefore, total number of arrangements together is equal to, now as we have taken 2p's as one entity, therefore total number of letters will be 5, therefore that will be factorial 5. Since 2 is are together, therefore as per that formula, therefore if we calculate, it will be 5 into 4 into 3, 60. Here 2 p's have been taken as one identity. Therefore, total number of arrangements will be 60. Now, in these arrangements, 2 p's are together, but we have to find here uh, number of arrangements in which 2 p's will not be together. Therefore, total number of arrangements when 2 p's will not be together is equal to total number of permutations without restriction minus this one. That means 180 minus 60 is equal to 120. This is the answer of the second part.